Hey folks, let's talk about the paired t-test from section 7.2 and 7.3. So hopefully you've already watched the instructor or the textbook videos that I posted. This video is going to summarize and elaborate on the same concepts a little bit. So just a refresher. We've already done the one sample t-test, two sample t-test, chi-squared test. The one sample t-test was last class, and today we're on to the two sample t-test. So here is some motivation for this test. Suppose we want to investigate the effectiveness of a certain drug. Piracetam, for example. Maybe you've heard of it. It's a popular nootropic, or also called a smart pill. So suppose we want to figure out whether it actually works. Consider the following two study designs. In the first design, you gather 100 subjects, 100 random people, and you randomly assign 50 of them to take a placebo and 50 of them to take the piracetam. You then perform IQ tests on both groups. So as a result, your data that results from the study will be two lists of IQ scores, 50 from each group, 50 from the group that took the piracetam, 50 from the group that took the placebo. And you can then proceed to compare the average IQ score in each group. So seems pretty straightforward, but consider this alternate design. So secondly, suppose that instead we only gathered 50 people. And this time we give each one of them either the drug or a placebo, and then we perform an IQ test, and then we give each person the other substance and retest their IQ. So in this case, our data will, well, depending on how we arrange our data, it will again consist of two lists of 50 scores. So on one of the lists, we could have the score of each participant after the placebo. And on the other list, we could have the score of each participant after piracetam. In this case, we have more information. So our method for this design will be to compare the scores of each person after they took placebo versus that person's score after they took piracetam, because in this case, it's possible to match the data into so-called matched pairs. There's a natural pairing between the two lists, namely the scores that came from the same person. Okay, so for the first design, we're going to use the two sample t-test, and I'll talk about that later on in this video. And for the second design, where we compare the data, that's when we use the so-called paired t-test. So for each of the 50 people, we have their score after the placebo, we have their score after piracetam, so we can take the difference in those two scores. We then get a list of 50 differences. So we just do a one sample t-test on those differences. The null hypothesis is generally that the mean difference is 0. And since we're just doing a normal standard one sample t-test, there's actually not that much that's new here. So in summary, for the paired t-test, we're studying the mean of the differences of the pairs. Right, so you take all the differences, take their mean. Oh, FYI, this is the same as the difference of the means. Not that that's important, but I don't know, just FYI. The difference of the means is the same as the mean of the differences. Moving on. The hypothesis format for the paired t-test is you have some hypothesized value of the mean difference, and it's usually 0. And the alternate hypothesis will be either two-sided or there's two possible one-sided hypotheses, as usual. the assumptions are the same assumptions that we had for the one sample t-test. So the CLT balance condition, for example, says that you don't want this list of differences to be highly skewed. And if it is, then you'll need to take a larger sample size. And the independence assumption means that, for example, you don't want a bunch of your participants, say, to belong to the same family, for example. Okay, so the name of this test is still the one sample t-test, or t-interval, except it's on differences. And our test statistic will be the mean difference, the difference between the mean difference and the hypothesized mean difference divided by the standard error of the mean difference distribution. And since we have a sample of size n and we're doing the t-test, this should live on the t-distribution with n-1 degrees of freedom. And similarly, we have our confidence interval formula where you take your point estimate and do either plus or minus the critical t-score times the standard error. Now, for the first design that I mentioned, which I said I would discuss second, we have a different situation. So this is when the groups are independent, okay? In other words, there's not a natural way to pair up the data in the groups. When this is the case, suppose that we have the following setup. Suppose that we have a sample from one population that has some mean mu x and a standard deviation sigma x, and we can take a sample, call it x bar, with sample size n1. We can calculate our sample standard deviation s sub x, and we will assume that our sample mean has approximately a normal distribution. Hence, it has approximately this normal distribution. Similarly, you have population 2 with a similar list of parameters and relevant quantities. We'll call the mean from population 2 y bar, the sample size from population 2 we'll call n2. Oh, by the way, notice that n1 and n2 don't have to be the same. In this case, in the paired t-test, definitely the size of your two samples has to be the same. I mean, if you're going to pair them up, then for sure you have to have the same number in each group. So in the independent case, they no longer have to be the same size. And our goal here is to infer information about the difference of the two population means. So a natural sort of best guess for what it should be would be the difference of the two sample means. What do we expect for the difference of the two sample means? Well, that'll be the difference of the two expectation values, but we've shown previously that the expected value of the sample mean is the population mean. So this is that, and this is that. In other words, the difference of the sample means is an unbiased estimator of the difference of the population means. Okay, good. Nothing surprising there. How about the variance? Well, the variance of the difference of the sample means, according to our rules for variance, is the sum of the variance of the first sample mean rather, plus the variance of the second sample mean. And as we've seen previously, the variance of the sample mean is given by the sample variance divided by the number of terms in the sample. So that's how we get that term, and similarly, that's how this one becomes that one. taking the square root, we get the standard deviation of the difference in the sample means to be the square root of standard deviation, the first sample squared over first sample size plus standard deviation, the second sample squared over the second sample size. So a likely test statistic would be to standardize by subtracting off the hypothesized value and, or perhaps I should say, subtract off the population, the true value, and divide by the standard deviation. So this is the likely form of our test statistic. Now, I can't fully justify what distribution this lives on. That's beyond the scope of this class. You might see it in Math 181B, but for now, for our class, we're going to make the simplifying assumption that this lives on a t distribution with d degrees of freedom, where the degrees of freedom d are conservatively estimated to be the minimum of n1 minus 1 and n2 minus 1. So when I say conservatively, I mean, it's actually possible to do better. There exists a much more complicated formula, but we're not going to use it in this class. So to keep things simple, we'll just make this the degrees of freedom in this case. And when we say conservative, we're actually using a smaller number of degrees of freedom than we would be using if we were using the more complicated formula. So as a result, we will have distributions with fatter tails and more uncertainty, which is to say we are playing it safe by making this estimate. So in summary, when we're comparing independent samples and trying to do inference on the difference of the population means, we will do a two-sample t-test if we're doing a hypothesis test, or we'll form the two-sample t-interval if we're forming a confidence interval. Our hypothesis format will be that the difference in the sample means is some number, which is usually 0. And the alternate will be the usual two-sided or one-sided alternates. We have a new assumption to check in this case. So the first assumption is new, and it's right in the name of the test. You need the populations to actually be independent of each other. The other two assumptions are both familiar. They're both what we already know to be the case for a t-distribution. So notice that the first assumption here says that the two groups are independent of each other. The third assumption says that the data themselves are independent within the group. So in other words, you need independence both within and between groups. As I mentioned, this long formula will be our test statistic. Okay. I don't want to say it. You can read it. I don't actually have to say this, right? Okay. So, and as we said, we will make the simplifying assumption that it lives on that t distribution, this one. And our confidence interval is probably the most brutal confidence interval formula I have ever written. And it's this long one. Okay, so if these formulas are getting to be kind of confusing, then let me summarize, because they all have the same basic form. When we did proportions, when we did means, and now that we're doing differences, they all start with, what do we call the terms in red here? Those are called point estimates. And then we pad our point estimate by doing plus or minus some margin of error, right? So these terms are the margin of error, and the margin of error terms all have the same form. They all consist of some critical value. Maybe it's a t-score, maybe it's a z-score. So These are the critical values, critical scores, critical values. Sometimes we call them T star or Z star. And finally, we have our standard error, which is our best estimate for the standard deviation of the sample mean. Okay, that's all I've got for now. And we'll do some class activity or something in class tomorrow. Hope to see you then. Thanks for watching. So let's see. Let me start off with maybe warming up or talking a little bit more about the a little bit more about the two sample t-test. Specifically, I want to talk about the distribution that the test statistic lives on, because it's kind of tricky and it's beyond the scope of this class really to get too much into it. But there's actually a question of even what distribution it even lives on. And what distribution it lives on can potentially depend on the relative sizes of the variances of the two samples, which is even more bizarre. We approximate the distribution of that test statistic with a t-distribution with this conservative estimate for the degrees of freedom. Let me talk a little bit more about that point, because that's maybe one of the more subtle aspects of this topic. So, FYI, here's the actual formula for the degrees of freedom. It's this long formula right here, which I don't even want to say out loud because it's so long. And you don't have to know it. I just thought I'd show it to you in case you're interested in what it is that we're not showing you. What you do have to know is that the one that we are using is a conservative estimate, meaning it's smaller. We're playing it safe by taking the minimum of the two sample sizes minus 1. So with that in mind, let's try a few yes or no questions. Suppose we have a negative test statistic and we're performing a two-sided, two-sample t-test, and D is the one that we use, the degree of freedom that we use. D prime is the more accurate one. In this class, when we compute a p-value by hand, yes or no, we approximate our test statistic to live on T sub D. Yes or no? And I've got a few yes or no questions here, so I would encourage everyone to get ready to answer. Okay, yeah, most people are saying yes, those that answered anyway. That's correct. Okay. Next question. Yes or no, our p-value is the probability that the absolute value of a t distribution with d degrees of freedom is greater than our test statistic. Yes or no? $27 people, let's see, 27 yeses and nos. Yeah, right. And this is all under the assumption that our test statistic t ends up being negative, and we're performing a two-sided two-sample t-test, and D is the one that we use. Okay, so this one appeared to be a bit more controversial. T is negative, by the way. So the event that the absolute value of a distribution will be greater than a negative. Hey, actually, we can even say exactly what this is. Ooh. Can someone tell me exactly what number this is? I already know what number it is. Yeah, that's just going to be 1, because this number is negative, and this is always positive, unless t is 0, but that doesn't have any area. So yeah, no, this is not correct, because the reason is we didn't account for the fact that t was negative. So it should be the probability that the absolute value of our test statistic is greater than the positive version of t, or equivalently, you could just put an absolute value sign on it if you want. Okay. Let me know if you have a question. Next question has to do with the 2 possible values of degrees of freedom. Yes or no? The probability that a t distribution with d degrees of freedom is an absolute value greater than the absolute value of our test statistic is greater than the probability that a t distribution with d prime degrees of freedom is an absolute value greater than the absolute value of our test statistic. Yes or no? You can see the T-Rex down there, which means it has something to do with that tip. And everyone should answer. What did I get? Like 10 responses? It's like a third of you. Perhaps I should draw this one before I answer it. So the t distribution, how about with d degrees of freedom, has a fatter tail than the other one. So let's say that's t sub d, and then the other one looks like that. So that's t sub d prime. It has a higher number of degrees of freedom, so it's closer to a normal distribution, and has a tail that's not as fat. So if we shade some areas, like let's say our t statistic is right there, so there's positive t and there's negative t, at least in absolute value. And if we shade the areas, then in green, we'll have this number. And how about in blue, we'll have the other number, which is definitely bigger. So what did I say it was? Bigger? Oh, okay, so I guess it's true. So I should put 2 up. Okay. Any questions so far? So finally, yes or no, using this conservative estimate for the degrees of freedom yields a bigger p-value, and hence we are less likely to detect an effect. Yes or no? Cool. All right. Good. Yeah. Bigger p-value means you're more likely to fail to reject. So in other words, you're going to need stronger evidence. So yeah, it's harder to detect an effect in that case. Cool. Okay. So I've got a Tyrannosaurus versus Gigantosaurus example. Here you can see a Tyrannosaurus on the left and a Gigantosaurus on the right, and a human in the middle for scale. Okay, so both of these dinosaurs are pretty big. They're more than twice as tall as an average human at the hip. Like if they stand up, they could probably be even taller than that, but just from the ground to the hip, they're like twice as tall as an average human, or even more so. So pretty scary stuff. In fact, we even live where tyrannosaurs roamed. Kind of interesting. They lived in North America. Gigantosaurs lived in Argentina, and the two of them did not live at the same time, though. So presumably they never met, but it seems like it would have been a pretty cool battle if they did. So this is the sort of question that we have paleontologists to answer, right? Like who would have won in a T-Rex versus Gigantosaur battle? In order to answer such a question, they need to figure out which one was taller. So to answer that question, they go and dig up some Tyrannosaurs and Gigantosaurs. They dig up 5 Tyrannosaurus rexes. Oh, fun fact, Tyrannosaurus rex means king of the lizard tyrants, which is pretty cool. So they dig up 5 T-Rexes and 4 Gigantosaurs and get the following feet measurements. Let's see. These were the ones for the T-Rex. These were the ones for the Gigantosaur. So we're going to do a paired, or sorry, not paired. We're going to do a 2-sample t-test, figure out if we can determine whether it's possible to say that one of them was taller than the other. And I think I'm going to have you all do it. Let's maybe try the Jamboard again. So last time I tried this, we had too many students to fit on it, but let's see, this is probably going to go disastrously wrong, but I think I'm going to have you try this problem. And okay, so I'm going to split you into groups for 5 minutes, and I want you to write your answers to A and B on the Jamboard, which I'll give you a link to in a second. And do it with your group. Explain it to your group if they're having trouble. You have to do a full test. That means name the test, state the parameter you're trying to study, state your hypotheses, check your assumptions, find a test stat, show your calculations, find a p-value, find a conclusion, and then try it in R using the t-test command, which is kind of a shortcut. But first, I want you to do it without using t-test. Okay, let me figure out how I'm going to do this. I'll split us into 5 groups. I need to share the link. So let me text that in the chat. Now there's 5 pages in the Jamboard. I'm going to make 5 groups. So group 1 should use page 1. Group 2 should use page 2, etc. Does it tell you the name of which group you're in? Guess I'll find out. Okay, good. Great, thanks, Jim. So, okay, go ahead and do part A. So write this down. Solve part A and part B on the Jamboard with your group. Write your answers there on the Jamboard. You can do it with your group. You can collaborate with each other. Use the page corresponding to your group number. Okay, so I'm now going to split everyone into groups, which means I won't be able to talk to you. At least not everyone. Or at least not easily while this is going on. Any questions before we start? Okay, let's see how it goes. Oh, you can return to them. See, folks are coming back. Let's see, room's going to close in 5 seconds. And I'll just show you. Cool. Okay. All right, cool. So I think everyone's back. Nice. All right. Good work, y'all. It's like most groups were able to correctly get at least part A. So I'll just quickly show the answer. So let's see. Name was the 2-sample t-test. The parameter studied was the difference in heights, difference in the average height of a T-Rex and actually it's a Giganotosaurus. Seems like they missed a cool opportunity to call it a Gigantosaurus. Instead, it's a Giganotosaurus, whatever. So as is typical, the null hypothesis will be that two means are equal, alternate being a two-sided alternate hypothesis. Assumptions, most of y'all correctly at least wrote down the 3 assumptions. Whether they are precisely satisfied seems pretty reasonable in this case. There's no obvious violations. I used R for the calculations. And the important one was the calculation of the test stat, that being the difference of the 2 means divided by the standard error term, which is the square root of the first standard deviation squared over n1 and the second standard deviation squared over n2, yielding a test stat of about 2.45. Is there a question?
Yeah. Does it have to be normally distributed? I thought the central limit theorem said, like, if it's skewed, if you get the means of the sample, it's still going to be normal.
Good point. Yes. So the underlying population distribution, or perhaps I should say distributions, because we're drawing from 2 different populations, need not be normal. They can be pretty arbitrary. But the less normal that they are, the larger your sample size should be.
Okay.
And yes, that follows, like you said, from the central limit theorem, because even if the underlying population is not normal, the sample mean will be normally distributed, at least for large enough n.
Thank you.
And yeah, and we're doing inference for the mean. That's the thing that we're using the normality for. So yeah, good point, good question. So there's our test stat, about 2.45. Our degrees of freedom will be 3. I saw that this is, most of you were correctly wrote that this is, according to our formula, 3 is minimum of 4 minus 1 and 5 minus 1. Good. So also, since it's two-sided, I'm going to take both tails, right? I plugged in the area of this one to R, but then I double it. At least that's the way I calculated it here in order to find the two-sided p-value of 0.09, which means this is a failure to reject at the standard 5% significance level. Part B was I asked you to redo the test in R and also get a 99% confidence interval and also comment on the difference. So plugging it into R, let's see. Here's the code for the t-test. I plugged in my 2 data sets, T-Rex and Giganotosaurus. I plugged in my confidence level, which only has an effect on the confidence interval part of the results, by the way. The t-value is still the same. What's different is the degrees of freedom. So they use, I'm assuming that they use the more complicated formula for the degrees of freedom. Note that it doesn't even have to be an integer. It's kind of weird. This is like the first time we're seeing non-integer degrees of freedom. The distribution still makes sense. There's actually a formula for the t-distribution that makes sense for non-integers. And with this larger number of degrees of freedom, we get a smaller p-value. Yeah, so if you use this for your degrees of freedom, this is the p-value you end up with instead of 0.09. So actually, we get a different conclusion now. We would have rejected the null hypothesis using this test, and we can state what the confidence interval is. So R gives us that this is the confidence interval right here. Okay. Any questions on this example? Then, wow, I know we, yeah, I said this was a long one. I don't know if I should do this second example. It's kind of a neat example, but yeah, I can save it for another time since you already worked so hard today. It is Friday and whatnot. So yeah, I think I'll save this example for another time. Maybe I'll put it on a test. Okay, that's it, folks. Have a nice weekend, and see you all Monday.